Dear students, in last two lectures I explained normal Zeeman effect and anomalous Zeeman effect. In normal Zeeman effect, as you can remember that I talked about ML, orbital angular momentum, and in normal Zeeman effect I explained that how if we apply a magnetic field then spectral lines give the three components. Similarly, in an anomalous Zeeman effect, when we include the spin, then we take mj in case of the anomalous Zeeman effect, which has also the effect of the spin quantum numbers. So, in that I explained you the number of lines which are obtained in the anomalous Zeeman effect. So, these two phenomena, normal Zeeman effect and anomalous Zeeman effect, here we are including the spin orbit coupling also in anomalous Zeeman effect. We are considering J equal to L plus S, and these two phenomena are basically for the weak magnetic field. But when we increase the strength of the magnetic field, what happens? So, the spectral lines which arises from the transition between the energy states, when the magnetic field is weak, then the vector L and vector S, both, how they precesses? They precesses around J, total angular momentum, and this J vector precesses around magnetic field B. But what happens when we take a strong magnetic field? This spin orbit coupling becomes little bit weak and the external magnetic field overcomes, and what happens? L and S vectors independently precesses along B. So they give the projection of the L and projection of S along the magnetic field B, and that's why they have the separate components, and then we will add the energy shift produced in the energy states because of this separately precision of the spin angular momentum S and orbital angular momentum L. Here I will explain you that when in a condition of a strong magnetic field, when S vector and L both precesses independently around magnetic field B, what happens? Then we can write, as we have written in normal Zeeman effect and anomalous Zeeman effect, we know this expression very well, that this is the energy shift due to the orbital angular momentum delta EL, which is the multiplication of omega L and the projection of L on the axis, which is Z axis. So we will take, and we know that E by 2m, so this is the expression omega L, and this is MLH cross, which is the value of Lz. Similarly, separately we can write due to the spin angular momentum, and this is omega S and then Sz, which is MSH cross. So these are the two expressions. So what will be there will be a combined effect of these two energy shifts together. We will take together delta E, which will be delta EL plus delta ES, and here you can compare with the anomalous Zeeman effect, that here we are getting a different term which is ML plus 2 MS. If you remember, there we get in anomalous Zeeman effect, we get the Landage factor G and we get Mj. So this one is different from that one. So now we can write term shift, which is minus delta E upon Hc. So if we write delta T, so we will get ML plus 2 MS, and this is the well-known Lagrange unit. So now you can compare with the anomalous, that this one here it only depends on the ML plus 2 MS value and not on the Landage factor and the B. Here B just only have included in the L dash. So now the final term is minus delta T is the ML plus 2 MS L dash. So if we take the same example like I have taken in anomalous Zeeman effect, so here in a simplified manner I will show first the table and the transition, and then I will explain it further that how anomalous Zeeman effect transitions for the D1 and D2 line, it becomes converts into the three lines due to the Paschen-Back effect if we apply the strong magnetic field. So this is the 2p term. Here it is 3 by 2 and half also. So I will explain it in my next slide. So it is 2p. So what is p? It is L equal to 1, and here I am not considering now J. Here S is half. Similarly for 2s, L equal to 0, S is half. So this is the number of level. How many numbers will be there? For ml we have 2l plus 1 values. For ms we have 2s plus 1. So now L is 1. So L is 1, 2 plus 1, 3 multiplied by 2, we have 6 states. Similarly for L equal to 0, S equal to half, we have only 2 states. So now what will the ml values? For L equal to 1, we have 1, 0, minus 1. For 0, we have only 0. And for the spin, we have plus half spin and minus half. And similarly plus half and minus half. So now it is these are the numerical just values of the ml plus 2ms. So here we can see the 2p states is split into 6 states. 2, 0, 1, minus 1, 0, minus 2. Similarly, S states is split into 2 states, 1 and minus 1. These are the selection rule. ml equal to 0, ml equal to plus minus 1. This 0, if the lines we get which is the parallel to the magnetic field, this plus minus 1 is for the lines which are perpendicular to magnetic field, and this is the selection rule for ms. So here now I will show you the example of transitions under the no field condition, weak field condition and strong field condition. Here I have taken the sodium atom. As you know, if we do not take the concept of spin, then we will just get the transition from P to S state. Since we get D1 and D2 lines in sodium, and that is because of inclusion of the spin. And then the transition comes from 2p half to 2s half and 2p3 by 2 to s half. And this is for the no field condition, and this is the doublets. If we apply a weak magnetic field means that this applied magnetic field is smaller than the internal magnetic field produced by the orbital motion. So if you remember, in an anomalous Zeeman effect, I showed you that there is the splitting in the energy states, and we have the mj value, and this mj value we have such type of splitting, and then delta mj is 0 and plus minus half, and we get that there are the 4 lines. Here 1 line, now we get the 4 lines for the D1, and similarly for single line we get the 6th line in D2. Now question arises, when we apply a stronger magnetic field, then what happens? The stronger magnetic field means that it is very strong as compared to the internal magnetic field. So the L and S vector processes independently around B, and I showed you the derivation, and then we get the value of ml plus ms, and that depends, splitting depends on the value of ml plus ms. Here ml value is plus half, plus 1, 0, minus 1, plus 1, 0, minus 1. For P, that is L equal to 1. For S L equal to 0, we have 0, 0. Similarly, S has plus half, plus half, plus half, minus half, minus half. So if we take these values, what will you have? 2 ml plus 2 ms. It will give you 2. Here it will give 1. It will give 0, 0. Here it will give minus 1. And then minus 1 and minus 2. Minus 2. What we will get here? ml is 0. ms multiplied by 2 will get plus 1. And again minus 1. So now we have ml plus ms. This is 2, 1, 0, 0, minus 1, minus 2, plus 1 and minus 1. These are the 6 states. And these are the 2 states I showed you in the previous table. So now if we apply the selection rule, ml 0 and plus minus 1, 0 is for, as told you, 0 for parallel, plus minus 1 for perpendicular. And if we consider the transitions, then we will get such type of transitions. So it will give you 3 lines. So this will be sigma, that is perpendicular component, this is again perpendicular, this one is the parallel component. So you can see that if we apply a strong magnetic field, it means the transitions line are with other components, which are several components. For D1 and D2 we have 4 and 6 components. Again becomes the lines as we see in case of the normal Zeeman effect. So applying the strong magnetic field, the anomalous Zeeman effect, the several lines vanishes, and again we get the 3 lines. So this is the whole phenomena explained by the Paschen, and which is called the Paschen-Back effect.